so unerring. There's something, dare I say, magical happening in chemistry that's been missed. So I'm going to tell you, we did this great thought experiment, and it's kind of like a microscope. And if you think about it with microscopy, the argument is if you go to higher and higher resolution, you'll see things that you miss, and you'll have a new understanding. So I just give you Anton von Leeuwenhoek's microscope. Apparently, in the Royal Society, they love getting letters from Anton von Leeuwenhoek with his microscope, this little bead on his eye, about little animalcules in rainwater, right? This, if you remember Pasteur, 100 years later, led to germ theory, right? So having this vision led to something new, collective understanding. What I'm hoping to show you, if I may be so bold, is this complexity issue you're going to see directly, right? So this is my animalcules going to this collective bigger picture, how biology works. So I think there's a propensity to say you're just showing pretty pictures of atoms. What I want to get across is there's a bigger picture underlying that we're trying to dissect this problem and see the underlying principles that lead to collective effects that we call chemistry and biology. Okay, so that's a fairly long-winded introduction. This is the first molecular movie camera. This is the first diffraction pattern. I think everybody here knows that you can connect this diffraction pattern to atomic positions. So for the students in the audience, 1989, 2002, 13 years it took. And I'll explain to you what happened. But imagine after 13 years, the way the experiment works, the sample sits here, the actors are atoms, we bring a laser pulse in here, we kick the actors to play out their scene, and then we bring a perfectly timed UV pulse to make an electron function, the Einstein photoelectric effect. You accelerate, in this case at the 30 keV, hit the sample, and this is where the quantum scattering turns on. Most beautiful manifestation of quantum mechanics there is. It tells you about the atoms. Now just imagine you're watching blurry-eyed 2 in the morning here, looking at that diffraction pattern, exciting probe, stitching together a movie, and you start to see those rings change, and you look at the timing clock, and it's 100 femtoseconds. That's the time scale of chemistry. That's that prefactor in the Arrhenius expression, right? So that's the moment the first atomic movie was filmed where you could see atomic motions faster than collisions, blur out the details. It was melting. We wanted to do something simple at first. It turned out to be bigger than we thought. I won't go into the details, but that first atomic movie will affect everybody in this audience at some point in their life because it figured out the physics for strongly driven phase transitions that led to the first method by any means to get to single cell surgery with no collateral damage. So you will, if you live to my age, you will benefit from this. There's something coming out in the clinic in about 4 years. Okay, so that's getting it going. This is what keeps me going. This is the underlying theme in terms of an intellectual focus. I'd like to get to take these atomic movies and then transfer that on to this bigger question about how chemistry scales. Okay, so these are the people who deserve the credit. The names in red are the ones who did most of the heavy lifting. I point out Carol Morse from Edinburgh. She was instrumental. I really want to show you the triadite problem. I have to show you this. It's 20 years of my life is into this story. And Carol was one who pointed out this neat bit of physics and theory that came together that directed us how to do this experiment to measure the first bimolecular reaction, like actually watch molecules collide. And then the other people involved in the red, I'll lay out their story as we go along. Okay, so this, for a chemistry audience, maybe this is embarrassing for me to say, but I'm going to be a little bit bold because I think I'm in the physics department, and you have to appreciate my predilection to tell you this is because in physics, I'm sort of overwhelmed with strongly correlated electrons, and so all new properties, supercolossal magnetism, superconductivity, always are related to some kind of collective effect involving strong electron correlations. And I remember thinking about this and go, wait, hang on. Everything in chemistry is electron correlations. When I teach first year chemistry, I have balloons, I tie them up and show how the electrons rearrange in space to lead to this beautiful symmetry, the hydrogen orbital basis that ultimately leads to us. Ultimately, at the end, this electron correlation leads to what I'm going to talk about. And it's very subtle effects that get cascaded over many length scales. And it's hard to see until now. We'll see it directly, right? So everything in is electron correlations. The other thing that's just a quick reality check. is you might think that you only have to worry about a certain bit of the molecule. Maybe we can just throw away most of it. No, right? So whenever you open an orange or a lemon, you smell something different, right? Obviously, they're the same molecule, one's the mirror image of the other. So clearly, the three-dimensional structure and arrangement in space really matters. It affects the binding olfactory receptors. So we're stuck with a problem where you have electron correlations. The full glory of the three-dimensional potential matters to how this molecule is going to function, right? And so you have inherently a high-dimensional problem, right? N atoms gets to 3 n dimensions. When n gets to be 10, things your brain can't keep up. There's so many possible permutations. If you go through the number of permutations, it quickly becomes astronomical. So you've got this high order dimension to chemistry. Then you go to transition state theory in about second or third year chemistry, and you think you get it, but then there's this underlying assumption of equipartitioning. So that means that the energy is all partitioned in all degrees of freedom. I have a high dimensional problem. How does it find the right path? And I have to say, my physics colleagues, if I ever have lunch with them, chemistry drives them nuts. Because how can it be different pathways? What's the underlying physics that sifts it to just a few, right? So this is what we want to figure out. And I will tell you that my organic synthetic colleagues, I'm glad to see some people here who can keep me honest, to the fullest, they don't care about what physical chemists worry about, right? They just go about their business and like named equations in physics, Newton's equations, Navier-Stokes equations that generalize effects. Our synthetic colleagues have discovered named equations that do the same thing over and over again on a similar moiety of molecules, right? Now, I'm going to back the truck up. So I'm going to show you something I think is pretty remarkable, but I have to say you don't have to do anything more than just use Baconian deductive reasoning. Chemists have discovered generalized reactions do the same thing over and over again. Chemistry is a science of speed, kinetic. My synthetic colleague, again, you can correct me if I'm wrong on this. You try to manipulate the conditions so that the reaction you want to have happens much faster than the side reactions. Everything's possible, but you're trying to condition and control the barrier, which gives you an incredible power. It's an exponential control knob on which pathway is statistically sampled, right? So with that, you can conclude that you find generalized reaction must do the same thing, right? We know it's a race against time. That means that this reduction, all the dimensions don't matter. This collapse in the dimensionality of the problem must happen at the transition state, at the barrier cross, at this scene. So we're going to go in with that as an understanding. I'm not going to oversell the case. We know that's must be happening, but how and why? Okay, so this is what we're after. How do we get this kind of control? And here's, again, apologies to my synthetic colleagues, but this is, I teach first year chemistry. I'm going to stop teaching this. But you can see here, it looks like there's a little bit of respect of the quantum mechanics in here with electron rearrangement. But you notice these mechanisms look localized. They don't treat the whole molecule. How is that possible? And there's only a small respect for the quantum. The electron can be anywhere, but the objective in these mechanisms is that it's highly localized. I don't believe these mechanisms anymore. I think they're mnemonic devices, but I've tortured first year chemistry students to come up with transition state structures, which I know right now can't be correct in its entirety. But they are useful mnemonic devices that help you stitch together different ways of getting a particular synthetic group analyzed. But basically, it's this arrow pushing exercise and simple rules that my organic and inorganic colleagues have developed over the course of time. And I really have great respect. Anybody, I remember, it wasn't Henry Falvey, it was, I'm stating it simple, they made cubing to make a box of carbon in the form of box. That was incredible. Henry Falvey, not Henry Falvey. Anyway, so here, what I want to get across, dissecting chemist's brain, this is the thought experiment. So chemists, by and large, I'm going to say this tongue-in-cheek, I would say we're kind of a strange group relative to my physics colleagues who have mathematics as a common language. I would say it's very difficult for a physical chemist to talk to an organic chemist. Physical chemists can't talk to organic chemists can't talk to physical chemists. we have some difficulty with the analytical theory, inorganic chemists, and nobody can talk to the theoreticians. But what I will say is the intellectual handshake in chemistry, like mathematics and physics, is this thought experiment. You try to imagine at the moment in space and time when you hit this critical point and you undergo a structure transformation. It's kind of amazing, right? You're transferring matter from one structure to another, and you're trying to picture that point in space, which is the crossing point, which is defines the barrier. So that knowledge or intuition allows you to come up with ways to control and give you exponential control. So this is our intellectual handshake that I think goes across disciplines. There's different variations of quantum and theory that go into how you treat this, but fundamentally we're trying to come up with a formalism to understand this special moment in space and time. And I'm showing you this here. This is my brain, not yours. This is this reaction, which is simple bond breaking of oxygen. This is supposed to be the giant red is supposed to be iron, depicting homolytic bond cleavage, where that little bit of force causes an entire night sky to rotate to their biological function. This has been driving me nuts for 30 years. And I'm not going to go into details, but this force is what leads to this coupling I told you about, this collective mode coupling. So I literally spent nights thinking about this picture and how it could transfer energy to the biological system, especially at the time we were thinking about this. Davidoff's theory of soliton transport of energy flow was thought to be the way, and it's not. Okay, so I just want to make one quick point because I take too long on this particular slide. This is the before and after snapshot of that Duncan moment I just talked about. This is from Prutz's Nobel Prize work. You probably can't see this very well. I want to make one point here. So if you look at this reaction coordinate, that knuckle is the iron. Oxygen is here. When the bond breaks, the electron goes to the iron gets bigger. There's an electron there now, and it pops out of plane. And if you look at that structure, before and after structure, it looks like the motion is along the mean normal. And so now, 1 minute tutorial in transition state theory, right? So this go back to Henry Eyring and Michael Polanyi in 1930s, coming with absolute rate theory. Imagine they wouldn't describe it like this, I'm coloring it up. Imagine I'm trying to convert my left hand into my right hand. I'm going to transform it. Doesn't go, right? What would you have to do? I'd have to break my fingers. That's going to hurt. I have to put energy in. That's one mode coordinate. Still not good enough. I have to turn. That's a second mode, right? And then you get to this transition state, which is like a kid's game. If you point to one of the fingers, I don't know which hand it is, right? You have a degenerate process. So then a small fluctuation collapses the wave function, and now you go over here. But that's the point in space, right? So I want you to kind of think about the modes, the critical point, and I'm going to come back to that. But if you think about that, you would say this, with this picture, you'd say, oh, this is easy. The transition state is just this doming coordinate, and it's halfway. Best known, I think people would argue this is the best known transition state. If you believe that, you're dead wrong. In 2003, with 4 femtosecond laser pulses, we showed that's not how that works at all. If I squeeze this, you'll see the problem. I usually have a cut, but you can see there's off-diagonal couplings. You can't have motion just like this. The full potential has to be involved, right? So it turns out the new 4, new 7 modes, the ring modes are coupled. Breathing modes allow the iron out of plane, and then that motion hits that helix, and there's the collective coordinate. And this is what I really wanted to see. We got scooped by Ilma Schlichting. I love her because in the end, they ended up seeing collective modes as just those last few. They did the experiment correctly. Okay, this is what got us going. This is probably the most important slide to get across the basic physics. So I'm going to take a very simple chemical physics approach. This is a very complicated system. I'm just going to use a mean potential. So this is going to be A going to B, and we're going to go across a barrier, and I'm just going to put a ball to represent the effective mass of all the motions. And if you do equilibrium fluctuations, right? This is the red ball. What would you see? You would see this, right? There are 3a minus 6. These are where it's harmonic. These are normal modes, right? If they're normal modes, these are stationary states. You're dead. Nothing happens, right? So the action of chemistry is here. So now you bring the ball up here and you let it go on this potential surface. Now what are you going to see? You're going to see this. High frequency mixed with low frequency. Go back to your quantum mechanics, look at the phase, look at the different wave functions and add them, and you'll find you'll get interference effects. This leads naturally to local modes. That's the collapse physics, right? When as an undergraduate, I have a paper in my undergraduate days where we were so cheap, we couldn't afford it. We only had a spectrometer, and we had to make very long tubes to make infrared measurements in the visible, which were overtones. And you saw this very complicated IR spectrum collapse to just a few modes. That was my introduction to local modes and the theory, and that stuck with me and helped us guide. So it's interesting when you learn as an undergraduate. There's hope for us. Anyway, we thought we could do this molecular movie business with electrons. Now, so just think about it. I'm going to have to speed up here a bit. Electrons repel each other. How in the world are you going to get enough electrons? I told you brightness was key. Just you think about high-speed photography, if you're trying to catch something faster, the shutter speed has to get narrower, narrower, narrower. Pretty soon you have no photons, you can't image. Brightness was key. We knew that. If we have any claim to fame, we knew back in 1989, the key technological hurdle was brightness. And the problem you have with brightness with electrons as opposed to X-rays, they're fermions, they undergo electron repulsion. How are you ever going to get enough electrons? We had lots of workshops saying we'd never be able to do this. We'd never get enough charge density. We'd never solve the T0 problem. We'd never be able to characterize our electron pulses. There was no methodology. From 1989 to 2003, we solved all these problems. And literally, they weren't solved until we had to spend, that's why it took 13 years. Okay. And now we're told we'll never be able to do solution phase, but we've done it. Uh-oh. Okay. Okay, I'm just going to skip over this. I just want to say the kind of funny anecdote for the students. One of my students, Brad Suick, after spending 3 years trying to make this electron gun, we call them, to do atomic movies, spent 3 years, nothing was working. We had a theory colleague, and he came into my office and he told me, this bleep bleep experiment was never going to bleep bleep work. And he proceeded to show me in the back of the envelope how this Fermi liquid theory that we used couldn't possibly catch the right physics. And then he asked me this question of every frustrated experimentalist. He asked me, could he do theory? I was like, okay, sure. So he did theory, came with a mean field theory, but this is I just want to leave you with this. This is 2002. This is an exact solution to the coupled equation of motion for 10,000 electrons. That's enough electrons to do atomic resolve dynamics. And what we saw shocked me. This is the pulse at birth. It's a 100 times a second electron pulse. This is the snapshot or window that we're going to use to examine the motions. And you can see with just 0.2 nanoseconds, that's just 1 centimeter propagation, the pulse is becoming highly distorted. I was so depressed into this group meeting. I remember going home thinking, this is it, I just wasted. I moved from Rochester to Toronto to do this experiment to get the startup money. My wife, when she found out that, you mean we moved from Rochester to Toronto to do electron diffraction? Well, yeah, kind of. Anyway, thank God she didn't kill me over the weekend, because after that, we figured out two things. The obvious dumb moment is if electron-electron repulsion causes the pulse to distort with propagation, just don't let it propagate very far. And we now knew from this calculation that our gun had to be just 1 centimeter big. And then before it was like the length of my arm, right? And the other one, you see this linear trick. The electrons at the front get kicked forward, the electrons at the back get kicked back. They don't lose space-time correlation, perfectly linear chirp. For the people who are optics experts, you start to salivate because you know you can use dispersive optics and compress. And so we have two electron gun technologies. Both technologies now operate. So since 2002, our source technology is on par with billion-dollar exos, right? In terms of this class of experiment. Because electrons scatter 10 to the 6 more strongly than X-rays. You look at the electron counts and the X-ray counts on our detector. It's as if we have a tabletop expo. Okay, so I'm just going to skip all the technology. I will tell you the real challenge for us right now. The technology's done. We can get electrons at ultimate brightness. You can't. The game now is to make them more collimated, more coherent in the transverse direction. Otherwise, you cannot do better than what we do, right? It's all samples. That sample was single crystal bismuth, took 3 months. The experiment took about 10 seconds to do. If we didn't have enough brightness, there would have been some pretty unhappy students. So brightness was truly key. It wasn't the electrons damaging, by the way, it's the laser pulse. Okay, so samples are everything. I can't get into the details. We just have a patent now on a way to laser crystallize nanocrystals on demand. So we think we've solved this 100-year-old problem for sample delivery for electron source technologies. So I would just go through. I want to give credit to Anatoly Yashchenko, who did the first electron diffraction capture reactive intermediates, and then Gerard Moreau did the photomission, which everybody followed, and then Ahmed Ziwell followed with low brightness that was sustained, but you don't have enough because you can't get the space-time resolution. And then we broke the picosecond barrier with enough electrons for full, even single-shot structure determination. Okay, so this is giving credit and nod to how this evolved. Okay, so this is the other way to go with fourth generation light sources. They're kilometer-long machines. I'm saying this, the X-ray community, these sources are great for X-rays and for biological systems where electrons are catching up. But for most of the problems, I would say electrons are better. They actually have much better signal noise, much higher spatial resolution. Rather than 1 angstrom source, it's 0.03 angstrom, 0.3 angstrom source, and so on. And the brightness now, you have to do these experiments with very thin samples. Otherwise, there's a mismatch and you have to go to too high excitation, which has been a problem for the X-rays. And so we're starting to rejig, the community starting to become aware that we have to converge to these realities of doing it under low excitation. Here's the first daguerreotype, first atomic movie. I don't have time to tell you about how that led to this new laser surgery process. That there is applications, but here, just look at the single diffraction order. That's right out of the box. That's really high quality signal noise. So we've gone from grainy daguerreotype to very high quality, like best pump probe data that gives you directly atomic coordinates. Okay, so now, I guess buckle up. Here comes a number of movies. I want to show you one which is going to make my point. This was the first atomic movie and molecular reaction, and I would say for my organic synthetic colleagues, this is one that chemists really, I'm calling chemists the ones who actually make molecules, and I'm a faux chemist. This is one that involves ring closing, so it's a bond formation. It's almost fine molecular, but it's constrained. So it's electrocyclization reaction. It's used commonly to arrange things in three-dimensional space. So getting back to our stereochemistry, right? So the question is, how does that ring close? There's so many different degrees of freedom. This is Erie's absolute brilliant work of these photochromic materials. In the UV, he put fluorines here to help us with drawing groups to make that bond photoactive. So you shine UV, that bond closes. Now look, it's more delocalized particle in the box and now absorbs in the visible. So you can shine UV on this, close the ring, make a bond, shine visible light, open it up, and you can do it many times. So this gave us a way to sample more. But still the issue, what are the modes? So this is the theory done by Mike Robb's group. I just want to tell you there's supposed to be a transition state barrier in between here. I won't go into all the details. Carol Morrison showed by revisiting this within a solid, we were able to get a slight hint of what modes were involved that really helped. So we did some high-level theory with Carol Morrison's group and following up on Mike Robb's work. And I don't have the full time, but I'll show you a movie. There's just a very slight tipping to the carbons that are going to form the bond. Then there's wave function overlap, and it just snaps closed, right? And there's 50 modes. Which ones? This is a homework slide showing that we can cycle up to 10,000 times. We can do power dependence to know what the maximum excitation can be. The data I'm going to show you is at 3% excitation, otherwise you get cumulative effects. I don't think there's any other method that can do it at such low excitation. Look here, this is pretty exciting. Remember I told you about 2002 and how this was really exciting for me. Diffraction after UV, you can clearly see the change. That was a hooray moment. Like it took years to get this sample to work. And you can see after pumping, we get it back. Watch here, we're pumping with red light, driving it back. Now it's ready, it's ring open, and now ring closed. And you can literally see by eye. This is a pretty grainy snapshot, but there's diffraction up to 0.2 angstroms. We have a lot of diffraction layers to fit, right? And this is Carol's helped us with this. We know there's a tip. We knew which atoms were constrained in how we do the fitting. And I'm just going to show you 4 modes. We could fit with a Pearson correlation of 0.93 to all the diffraction orders. And this is, you're going to see here, it comes in and it just snaps closed. So these steric hindrances that people use to direct chemistry would never have the time. So I'm wondering if a lot of the effects are not electron withdrawing effects. This is the one I want to show you. If I only get past this, I'm done well. That's how much time? No time.
Well, 5 minutes.
Okay. This is platinum DMIT. It's the size of a protein. In terms of structure, it's electron transfer. We can photo electron transfer. So it's the simplest chemistry. No bonds made or broken. It's just reorganization. There are literally hundreds of modes possible. We can put in like going back to my hands. If I know which finger lengths are the same, I put them as constraints. We learned this trick from the Higgs boson experiment. So we put it, this is a physicist, this is treated. There's data because they didn't have enough scattering. So we picked up on that. We used the same trick. And so what I'm about to show you, these known bond lengths and angles act as constraints and phasing centers. So I'm about to show you it's not a molecular dynamic simulation. It's not a model fit. It's direct, unique Fourier transform to real space, real deal. So I'm showing you the atoms as stars against the night sky to not bias you. So the bright star is platinum next to sulfur and nitrogen. So watch, I'm going to click. You see the atoms move. Okay, watch again, click. Right? That should be amazing to you if I can put words in your mouth, because if it had been all possible motions, it would have been a blur like angry bees. It's not. Okay. So you literally can see by eye, if you look from here to here, click, you can see platinum is the bigger player. And the reason now the light bulb goes off, the electron density changes largest there. The motions involved that fluctuate the electron density are the ones that form those reaction modes. So a problem with 100 dimensions reduced to just 6. And look at the resolution. This is the bond length, 0.1 angstroms. Our noise floor is 0.02. We're literally measuring the change in position of the atoms and less than the thermal noise. So we've achieved a fundamental space-time limit to imaging chemistry. You're at the noise floor, right? So this is really the best you can get at, and we can see this collapse. Okay. Now I have to show, sorry, I'm just going to have to, I have to show you, these are some stars from your institute that were in my group. I just showed you this collapse to just 6 modes. I can tell you now better why this is. We understand now what the underlying physics that leads to this collapse to just a few key modes. And we've extended this now to bigger systems. This is iron 3. This is Leticia Gomez's theoretical, which I don't have time to go over. I just want to show you that we've done this open shell iron 3 system and that was done by one of your students, Sumajit Mitra, right? And he did graduate. And he found this really incredible thing. We see now there's spin orbit coupling. This is going from a doublet to quartet to hextet, and we can resolve this optically. And what he saw after doing looking at residuals, you get these oscillations. These oscillations have a growing in. It's a coherent mixing. We see 2 different frequencies, and we see these coherent mixing through the difference terms. And so we're seeing in this nonlinear region where you're far from atomicity, the potential is really wild, and it's coupling these modes to give you these sum and difference mixing. So we're really seeing atomicity. So that's the new bit of it. And the other thing we figured out is the vibronic coupling. If you think about it from an electron transfer standpoint, it's not just spin-orbit coupling. If you think about it as charge transfer, it's the electron the modes that cause the change in electron density are also influencing the fission probability. So this is kind of a new tweak. And this is his diffraction data. And if you thought this was a coherence artifact or some optical trick, which I thought, I didn't, what's going on, we now see it in the electron diffraction. So you can see this in the low Q region. So this thing is scurrying around on this highly harmonic potential, and the modes are undergoing all kinds of frequency combinations. And then Nita's work here is on polarization coupling, we're just writing it up. And she's been able to look at wiggles here and here that lead to these huge changes in magnetization in this system. So these are your students that work with me. So I'm very glad to be here to congratulate you on these kids. I think I'm gonna leave out the I3 problem. I'm out of time. I would just say that this took 20 years of my life. It's the classic I3 collided with I3. We photoexcited, broke the bond, shot it across. If you try to think, how would you ever set this up? You see the iodine hit the other I3 and ring like a Newton's quantum cradle. And we see the other bond contract. So we see for the first time the full atomic details of a bimolecular reaction trajectory. And you think about how would you ever set this up? So we now have done the classic thought experiment using I3, which is again the classic case. Okay, so I didn't have time to go over all that, the data analysis and diffraction, but this is what I was talking about here. So we see these in all kinds of systems, 6-3 modes. This collapse to a few key modes is a general phenomenon, and it's on every system we've seen, and we can start a piece about why this is working. And I just want to say in summary, we now see the direct observation of strong vibrational mode coupling, and this is this magic of chemistry. We now can understand this. If you think about all atomic fluctuations are going to lead to fluctuations in electronic levels, but not all atomic fluctuations are equal. Some really modulate the electron density, and it's those that are causing this collapse. And ultimately, as we scale, I would have loved to talk to you about the next phase in our research program, but we have a new idea about how to look at this in biological scaling terms. So we can now go inside the cell. We don't have time to talk about it, but we can now look at these same kind of issues, but now inside the cell. Okay, so ultraviolet electrons, like sending probes to transition state, like the rover sending back pictures of Mars, we can now do that. And yeah, beyond this grand challenge, we're actually just beyond chemistry. And I have to, as a conflict of interest statement, my university requires me to tell you that we started a company up because people are having a hard time getting electron guns developed. And so we've now decided between myself and Herman Scanning to make these available with student training and software every day. So we're just going to make it completely open to everyone. Okay, on that, thanks very much.
Lots of very exciting data and a lot of work. So let's boil down some questions, key questions.
Very nice, great. So I want to ask you two things. One is, of course, when you're going to cells, you must be looking in solution systems, right?
Sorry, what?
You're looking in solutions.
No, these are all single crystal.
These are, but when you're going to look into cells, then you would be going into solutions. How would you?
Yeah, okay, so here's the idea, because now you see the problem, how chemistry scales on the molecular level. Now, the next question is, inside the cell, if you calculate 100 nanometer voxel, which is the chemical mean free path, like you think, how long does it take a molecule to enter the cell before it reacts? It's about 100 nanometers. So if you want to understand how chemistry leads to living systems, you have to look at spatial correlations on that scale. So we now see on the molecular reaction level, there's spatial relationships. Inside the cell, if you think of the number in 100 nanometer voxel, the chemical mean free path, there are 10,000 proteins. There's no string holding them there. It's the number of possible permutations is mind-boggling. So you know just that what we learned here is there has to be spatial correlations. And the driving force for biological systems is the free energy. We had effectively zero information on the spatial correlations of free energy inside the cell. So if we could go inside the cell and measure every single molecule, then you would see A plus B goes to C. But if you only have C, it goes the other way. We can determine the spatial relationship of the free energy that drives the cell, and then you need to put the kinetics on. But this is what we now can do. That first atomic movie, we learned how to ablate. It turns out all the molecules that come out are fully intact. So we can go inside a cell and we can take 100 nanometer voxel and go into a mass spec. So our electron gun, if you change electrons to ions, it's the same technology. So we literally now we understand the chemistry bit. It's the spatial correlation inside the cell that
So you're not talking about the diffraction inside cells?
No, inside there we want to go in and literally take a cell and and get intact molecular signatures. And we have maybe 10 papers showing that this laser trick gives you 100% retention of the molecular signatures.
Can I ask another question?
Are there any questions? So first, let's she can continue.
Okay, quickly.
Okay.
So when you look at crystals, like when you're looking at reactions, often because of close packing, the way in which molecules react is going to be different from solution.
Yeah.
And also you're coming with the electron gun. Are you, like, is there any way that you can perturb the reactions or the reaction that is going on in the crystal?
Yeah, no, the electron is the actual scattering is too short. It's on the sub-femtosecond time scale. So that is not a perturbator probe because the electron doesn't hit the same atom. Another electron doesn't hit the same atom. They're all interacting with different atoms. And the scattering time is too short for them to perturb. So it's a non-perturbative probe. And a lot of times you have electron-induced damage in TEMs. We can literally, because our fluence is so low, we can have a sample hit for months and see no deterioration. So that's not a problem. And what was the other point?
First one was like, in crystals, sometimes.
Oh, yes, okay, so, yeah.
The way in which reactions happen is different from what you have.
We do theory where we embed it, but what it turns out is it's kind of remarkable in that, for the most part, the things you see in solution are virtually identical. The dynamics are slightly different, but the motion involved looks to be very similar to what we can tell taking optical data, comparing it directly to electron diffraction data. Where we do see differences is if you hit, what's really interesting, this is how molecular property probably happen. If we excite a crystal too strongly, like we have a near neighbor that's also undergone a reaction, then we see changes. And so we have to go to this really low excitation limit, which I think only electrons can really do. But it's a good question. We were worried about we had this discussion over lunch. I was really worried about excitonic coupling, and that seems to not be the case.
Yes, so very nice data. So I have a question about the wave packet growth that you showed.
Yeah.
So is it possible that
Yeah, that's what we get.
Oh, so that's how
That's what we did.
Oh,
That's exactly. The way I'm looking at it, it's like nonlinear mixing in optics,
Right.
where the nonlinearity is the nonlinearity of the electron polarization. Here it's the nonlinearity of the atomonic potential which the molecules are living in.
but in that case, the phase are constant, right? If you think about the nonlinear optics mixing of two.
Oh, there's no phase, we don't need phase matching for that. Because you're looking at growth and
Yeah.
you don't need phase matching. When the light comes in, it's undergoing nonlinear mix. It's whether you can measure it or not. So you need phase matching, so you have constructive interference. So the nonlinear effect responsible is something that's measurable. In our case, the molecule, it's happening on the molecule itself, and the change in optical properties is sufficient, we can measure it.
Are there, yes, okay?
So
Yeah.
you really got me thinking, actually. I really enjoyed your lecture. But I was wondering if you ever envisaged taking the same material, but different crystal packing.
Yes, it's hard to do. If you have a system, we'd love to look at that.
Because that would usually involve different collapse. Or maybe it would be.
I think the intramolecular, I think getting back to that other question, I think the intramolecular potential dominates. Because again, the weakness in our method is we're always looking at kind of unimolecular process. Only the triadi can we have a collision. So we're looking at what is a molecular centric or molecular reference reaction. The intramolecular potential is going to dominate. So the intramolecular potential is a minor perturbation, and we can compare quite closely to the solution. We have seen lattice effects that lead to different dynamics and even different modes. So there are effects.
So that's what I was thinking, because the best way of going about it is if you take a charged species and then you have a counter,
Yeah.
and then you get very different results.
Oh, we did that. Sorry, we did that. So there's this molecule called EDO-TTF, which actually is superconductivity of one ion or non-ion. It's an organic charge transfer system. We changed from phosphorus hexafluoride to antimony. Way different. Like
That's
where
what
the ion, the heavy ion, as the ions moving in to stabilize the reionization, because we figured about at least I forget about the counter ion. So the counter ion's moving in, it's repolarizing the medium, and they dominate. All the other modes look like shadow projections on that ion. The ion motion totally dominate. We have done.
Okay, there's just one last question I have. How far are we from engaging the inorganic and organic chemists in looking at diffusion-mediated reaction and watching them? So this is
good
going to
question.
be difficult to do it in a crystal. I'm asking,
Yeah, solution.
Yeah.
Yeah.
what's the modality
have-
for that?
There's so Christian Mojave and my group are collaborating, and so we have nanofluidic cell devices that we can look at in solution type. But we'd be using diffraction. So you want to watch diffusion.
Yes.
There, I think, let me just say, I can see if you set up the system correctly with a inorganic, organic.
Metal complex.
Something to give you enough context, yeah. I think you could do real space imaging on this. We have a new trick. Where we have a lab technical detail, but we have a lab 6 nanotip. So very high coherence length. When you're talking about the time scales involved are more like microsecond, millisecond.
Right.
You take this, we're getting this built up now. You take a very long, you can take a laser pointer.
Right.
And an AO, it takes virtually no energy. You generate a microsecond pulse and then you spatially image. You have enough electrons for atomic reconstruction. So I think probably within a couple of years, you're going to start, what will probably happen first, we've been pushing this for such a long time. What will probably happen first is you'll do in-liquid imaging of biomolecules.
That's easier,
Right, that's going to be the high impact first step.
But
then next-
Proteins.
Fruit, yeah, and then, yeah. And then I think the next after would be looking at spatial.
Spatial
If you look at, because somehow inside the cell, it becomes, the diffusion has to become spatially correlated, so.
Right, that's right.
I think you could definitely do it in a couple of years.
Sure.
Sorry, this is it's 100 nanometer, the microfluidic.
Yeah, all the stuff I talked about, maybe people didn't appreciate why this is so hard. You have, the one problem I told you took 20 years, it was the sample. So you have to get the sample down 100 nanometers thick. So the liquid cells are silicon nitride, 100 nanometers, very cute trick from Christian Mojave. We have our own trick, which uses phase diagram you break a seal and then the liquid gets sucked in with capillary force, and rather than bulging, it deforms, it keeps it thin. So I feel we solved the liquid problem.
Okay.
The one thing I will tell you, which is really, if I can say cool, we think we've solved the problem. The big problem is always 100 nanometer samples, always. For 100 years with limited TM as the sample. We can take a femtosecond laser, you can give me a drop, and we can come in and we can make 10,000 crystals out of that, right on the TM grid. So we've solved now how to make the nanocrystals. You can literally laser write the nanocrystals. So this is where I think we can help organic chemists. We can do high throughput structure. If you make a molecule, you can hand it off to us. We need micrograms, and we can tell you what the structure is with all the hydrogens.
Okay. Thank you very much, Dwayne. As a mark of appreciation, could you come in front? We would like to, maybe it's not, maybe here. Just on that side. Yeah, so this is a book on the TFR collection, and it has all the paintings that we have. Looking at, even if there's a small time, just go around and do it.
Thank you. Thank you very much. Thank you.
Okay, so next up after this talk is Professor Devashri Ghosh. Yeah, you need to, so in the meanwhile, I'll just have 2 lines for Devashri. So Devashri is a professor, is a senior professor at IACS, Kolkata. Yes.
Those who want to keep my lecture?
Okay.
That was great. No way. Sorry, I don't mind if you.
You focus on introducing her.
Yes. It's it's called Ubuntu. Yes,
Ubuntu.
yes. And there's a zillion files. I'll find mine.
Okay. Okay, so I only have 2 lines, Devoshri, that's why I will finish up quickly. So Devoshri actually has been doing some incredible work looking at excited states for some time. And some of her work has involved DMRG methods, which would enable people to look at, in very large systems, you can look at even things like triplet states, which are hard to compute for large systems. And we have been closely working in recent times on a problem of Singlet exciton fission. But just to tell you the impact and reach of Devashri's work, Devashri actually, just to say that in the last 5 years, she has been awarded the International Academy of Quantum Molecular Sciences Medal in 2021 and the Popel Medal in 2025. So with that,
Okay, thank you, Jatishwar, for that kind introduction, and definitely thank you for calling me here because this is a whole lot of fun. So actually, I am very jittery after your talk because you talked about so many things, and I'm going to talk only about fun stuff, and that's it. And I will just tell how many difficulties we have faced in that one tiny part. So before I go into singlet fission, see, I thought that is this thing. This is not working because that's the
thing. So we have to put in that. So do we put your stop in the?
Yes, sure. You can put it in the desktop or wherever. It's a DOS 202.
You have to insert that, right, somewhere?
What is that? So let me.
Put it the desktop. Doesn't matter. That I do. That's for computer.
Photographs.
Yes. Yes.
Okay, so now it is in.
Yes. But that whole thing.
No, this is not meeting.
Yes.
Yes.
Okay. Thank you.
Sorry.
And sorry for taking time to set it up. So before I go into singlet fission, let me kind of give an idea of what we are really interested in. Actually, I am interested in excited state chemistry. I am generally a very excited person, and I like excited state reactions because, well, they kind of defy many of the chemical principles that we swear by. And that makes it kind of cool. But what does it entail? Understanding excited state reaction or even excited state physics. It's essentially a potential energy surface that looks like this. But as it was mentioned in the previous lecture, it's actually not two-dimensional or one-dimensional like over here. It's a 3n dimensional surface, or rather 3n minus 6 dimensional surface. But essentially, we kind of boil it down to something like a reaction coordinate or a collective variable or something like that, which is a very complicated direction, and it might even keep changing along the way to wherever it is happening. And if for the students, if you are thinking where this picture came from, this is actually a slightly fleshed out version of what we are familiar with as the Jablonski diagram. So, if a molecule gets excited, it will get into its optically allowed excited state. In this case, I have somehow put S1, it could be any other state. And because if you are kind of thinking along the Born-Oppenheimer surfaces, then the molecule will deactivate along some vibrational degrees of freedom. It might encounter some crossing points or conical intersections Via those, it can go to some photoproducts, it can come back to the ground state, it can go to a triplet state, all sorts of stuff can happen. It can also radiatively just, give out all that energy and come back down as fluorescence or phosphorescence. And each of these phenomena that you are seeing over here will have different time scales. And that's what a spectroscopist like Jyotishman will measure. And from those time scales, we'll kind of try and backtrack and try to see what is going on in that molecule. The thing is, I might even be interested in not just a molecule. It could be a molecule in a protein mech. It could be multiple molecules interacting with each other weakly, strongly, you name it. So all of this is just going to add different layers of complication to this picture, which ideally looks simple. In fact, it is much simplified from what it really is. So that's what I aim to understand for the phenomena called singlet fission. And now this is kind of a motivation for why one would like to understand singlet fission. Actually, the reality why I would like to understand singlet fission is none of these. I find it really cool, so that's why. But to the funding agencies and stuff, you have to say that solar cells are very useful. That's fine. No. So anyway, so that actually bumps up the efficiency of traditional solar cells when used as a hybrid material. Now, what is singlet fission? Actually, the phenomena as such looks very simple. If you have multiple chromophores in close proximity, which you would have if you have like a molecular crystal, or even if you have some kind of aggregates and stuff like that, you have these multiple chromophores. Light is incident on those chromophores. And let's say one of those chromophores gets excited into its optically allowed state. And it so happens, because there are so many other molecules, same chromophores next to each other, they decide to share the energy and form two triplets. And now I know that this is actually not a great depiction of the phenomena, because here I have mixed the idea of orbitals and states, but because it's just easier to see it this way. But I mean to say that there are singlet states, and from there you can go to triplet states, and the triplet state would have a orientation. The triplet pair state would have an electronic orientation that might look like this. And so the final triplet pair state is still a singlet. Therefore, it's therefore it's a spin allowed process. And essentially, what one can think about in a very naive way is this energy criteria. But the reason along the talk, I'll explain that we should not put too much into this energy criteria, because after all, this excitation is not going to be exactly on one chromophore. It's not going to split into exactly two chromophores. And none of this is going to happen in such a neat way. But we would like to look at it in a simplistic picture, and therefore, maybe this is a nice starting point. We will see where this starting point is an okay starting point and where it might not. And of course, we would like to know about the mechanism of the process, and if possible, at some point, find suitable singlet fission materials. And actually, this work that I'm going to explain